Good morning and good afternoon and good evening to everyone. My name is Isabel and I'm from the video marketing team. And first of all, I want to wish you a great and successful 2021 and a great start. And you are actually already making a great start because today you are joining us for this webinar and to learn about the metal cutting world. We're going to share tips, strategies, and our presenter Mike will also help you choose the best products and solutions for yourself, your company, or your customers. But before we start, a few words on safety, because this is very important for our corporation. I want to make sure that you are all safe and in your environment, the place where you are, and also that you are taking care and following the local rules and regulations. So today, during our webinar, our metal cutting expert, Mike Sperake, is going to teach you how to overcome challenges when machining stainless steel and high temp alloys. And he made it very interactive, so we have many videos for you, success stories, as well as other resources like catalogs. You can find our main all-star catalog with our products in the handout section, so you can download it whenever you prefer. And if you have any questions, we will be having a Q&A session at the end, around 15 minutes. And so feel free to write all of your questions throughout the webinar. And then at the end of the webinar, we also have a survey, and this is very important because this webinar was actually organized because you requested us to cover this topic. And therefore your feedback is very important. One last thing, this webinar is part of a two episode series. So for the second episode that is going to be about hole making and turning, I will leave the link in the chat so you can also register to that if you didn't have the chance to do it before. So we have a very interesting and we have a lot of session with a lot of things to teach you. So Mike, I will leave it to you and we will be speaking later during the Q&A session. Enjoy the webinar.
Thank you very much, Isabel. Good morning and good afternoon also from my side. I hope you are in a safe place and you feel very comfortable now. Maybe have a glass of water or coffee beside you, and hope you can enjoy our training today or webinar today. Well, we were thinking it's very interesting for you really how to machine really stainless steels and high temp alloys. And I will first introduce a little bit of WIDIA because I'm not sure if you all know WIDIA, and therefore I want to introduce a little bit about the background and why it shows a little bit interesting that you have especially for WIDIA looking at that. First of all, WIDIA, the name is coming from the German like diamond, so means wie Diamant. It's really a very interesting name where it's coming from, because our former owner company Krupp founded us in 1925. So you maybe know Krupp as a stainless steel producer. They were very experienced at that time, really to introduce materials like these kind of things. They were one of the first ones who have nickel-based stainless materials. And so far, they are very experienced also to really introduce the carbide itself. So we were the first ones really were able to produce carbide in the modern form, like a sintered product. And we started with that in the 1925. And from then, we were really producing carbide. And still our plant, what you can see here on the picture on the left side, is existing. And we are still using that for making inserts. So it's still in the center of Germany, and so we can have a lot of experience used for not only for the the carbide itself, also for the produced materials. But nowadays we are also not only in Essen and in Germany, we have also a plant since 1967 in India. We have for sure the plants in US, and then the last years we opened up also a plant in Vietnam to cover the local market needs. You might say, well, Vietnam is not really a good technology market, but still this market is very interesting because also companies like Samsung are producing their mobile phone cases there, and therefore it's also for us very interesting to to have a plant down there. Yeah, let's go a little bit to the topic where we want to start with. We want to go through the stainless materials and the high temp alloys, as these materials are in the content of the materials are very strong relatives, and the behavior, they are really very strong relatives, for sure on a different level, but nevertheless what you can learn with stainless steels you can transfer to high temp alloys, for sure in a different sense, and therefore these challenges which need to be solved are very similar. And if you understand where the challenges are coming from, then it's easier to understand how to machine these materials. For sure, we'll show you from our experience what is possible also with our tools, and which kind of applications we already solved very easily with our tools, and then speak a little bit about special grades made for these kind of challenges, and also some of the products where we can really promise you that we can be successful in these kind of machining processes. Yeah, let's look a little bit deeper what is important for really the situation. What kind of materials for machining is important? What kind of properties are necessary to look at? And the first ones are for sure the physical and mechanical properties, which is the tensile strength, the hardness of the work piece and material, the ductility, for sure the heat behavior, which is very challenging, especially in the high temp alloys and stainless materials. Also abrasiveness, so means also gives us a good indication how fast the insert or the cutting edge will wear. And for sure also that ends up in a very easy to handle property, which is called machinability, which condense all these kind of properties together in one number or in one value to make it easier to understand to really how to machine it. Yeah, basically a lot of alloy components have for sure effects in the materials, and we are talking mainly about metal cutting here. We are not talking about really on plastics or other materials. So usually metal cutting is really having a combination of these kind of materials, and most of the materials are integrated in the alloyed components. But especially for the stainless materials and the high temp alloys, it's very important to understand that they have a higher content of chrome, maybe nickel, and maybe titanium. That is very important to understand, because these three components gives for the workpiece itself a lot of positive effects, but is also having a lot of let's say challenges for the machining process. And if you look especially on the materials itself and look at the volume of cobalt, chrome, and nickel and titanium in these kind of alloys, then you really get a first indication of what you need to do with the cutting tools and with the machinability and with all of these kind of environment. Yeah, digging a little bit deeper in the stainless steel materials. Well, the stainless steel arena starts from the P series. Well, you should say, well, stainless steel is M, yes, but some martensitic and pH materials are really in the P series, and also more or less the stainless steel. What I will say, what I want to say with that is that if you really think about how to machine these materials, it's closer to the stainless than to steel or cast iron. So it's very interesting and important to understand that these kind of materials are really a group of M materials, and the way of machine it is the logic behind is more or less the same. There are three different portions in the stainless arena. The first one is this austenitic stainless steel, which is common names like 3 or 4L, or in European designations like 1.4301 or 407, which you can find very easily on the workpiece descriptions. But also for sure, we have the higher alloyed, high strength austenitic stainless and cast stainless steels, which are gathered in the second group. V2A and V4A are names from Krupp. And in Germany, for instance, is V2A and V4A for many people very easy to understand name for these kind of materials. I know that in every country is a little bit different which kind of naming they use. In US and US-based countries where this material appears, you find these naming like 316, 304. Also sometimes in UK you find that. I know that France and Sweden has different names because they have different backgrounds for the naming. Sometimes it's covered a little bit more or less to the same designation. So a transfer from one designation to another one is sometimes a little bit challenging. So it's very important to look really on these components in that. And the old German classic way to name it gives you a very good indication of it. You see here the chrome content is 18 and the nickel content is 8 in that case for this classical V2A. So you see already there's chrome and nickel in. And what I said before, we have to be careful. Heat and ductility is a challenge then. And then if you go to the next stage, which is then the super alloys, heat resistant alloys, you have this situation that you have iron based, so means also on this kind of iron main component, and then you get it with cobalt, nickel based, and titanium based. Very interesting that the nickel and the titanium based alloys are very common nowadays because you need it for really heat resistant situation. You need the nickel based alloys, and for very light components you are using very often the titanium alloys because they give you a lot of very nice advantages in that. Yeah, it ends up all in a big database, and as we are not only having the database from Krupp, also part of our company is ATI, where a lot of heat resistant materials are produced, and so we have a lot of knowledge about how to use and produce these kind of materials, and for sure we have also the knowledge how to machine it. And it ends up that we have really a very good overview of nearly every available high temp alloy in the market, because we have more than 770 different materials really in our database, where we already made a lot of investigation how to machine it and how to understand really the cutting edge. That ends up for sure also in the experience what we show up in Novo to make it easy handle for you. And for sure we are using then correction factors, what you can see here in this table just as an example, what is for sure integrated in our databases. When you really look for cutting data of our tooling, you will find easily these kind of information, and that gives you a good indication of what you need. You see already in that table here that you have a variance which is pretty high on the cutting speed. That's first dedicated for sure on the radial engagement, and this is a topic where I come later to. And for sure, it's also dedicated to the overall situation in the workpiece and the coolant situation, and for sure also in many other things like how long I'm machining this material and how good is that really taking away the heat. Looking a little bit for stainless steel, we see here that we have really very easy to handle these kind of factors in machinability. So if we have really austenitic material based on 100%, Then we go for martensitic, which is much easier to machine, like a 4305, which is already based in the P5 group. Then we have really duplex materials, the PM3 group, where you see 14462 and higher alloy duplex materials. Then for sure these really challenger materials, also like pH materials, also based in the P6 group. Yeah, if you go then to the nickel-based alloys, you see the same thing also here, that you have really the same classification based from Inconel 718. Then you really go to higher alloy materials like Udimet or Rene, which are for sure names, and you have to really look for the really alloy components in the direct database then from the producer. And you have also materials which are easier to machine, like Inconel 625 or Monel 60, and it makes it easier to understand really where you are. Coming a bit to the titanium and titanium alloys, which are grouped here in the S4 group. Also there you see that titanium is easy to classify in these kind of groups, like the standard titanium here, titanium 6 for V, which is given here as 100% machinability. And then if you go to the higher alloy, like the very common titanium 5553, which is just 60 to 50% machinability. That shows directly usually also in speed. Means if you have already really titanium as a basic stuff with something like 50, 60, 70 meters on speed, then you really have to half of it if you just change the material under the same conditions. That's meant by when I show here 100% or 60 to 50%. Titanium is also a very tricky material because it shows up with a high ductility. Ductility is easily to understand if you have if it's like a gummy material, and you can understand that it's not easy to machine because you need to have a sharp cutting edge, but at the same time you have to have a very stable cutting edge, because the sharp cutting edge has also the disadvantage if it is sharp. We have a very high heat in there. It's going to not easy to get away from the heat, and the problems occur really at that cutting edge. So that is really very, very hard to understand, because also if you have a high ductility, you have also the problem that you have long chips. For milling is that not the major problem, because for sure is always the process is already giving you a certain short chip. It's more problem in hole making and in turning, where you really have massive problems than with these kind of long chips. And with gummy materials, it's you create in turning processes and something like a spring. Yeah. The next big challenge in these kind of titanium alloys and titanium materials is for sure the thermal conductivity. If you compare it with steel and stainless steel, the thermal conductivity is extremely low in titanium. What does it mean? Means the material takes not over heat. So the theory behind when you have a cutting process is you machine, and the chip get all the heat and takes it away from the machining process. But if the heat is not going in the chip, the problem is the heat is going into the cutting edge and into the workpiece, which is not wanted, because for sure the workpiece can be disformed by the heat introduction, and the material of the cutting edge is also for sure limited somehow on a temperature, also not nice. So the end of the story is you have to go down with cutting data, mainly with the speed. Yeah. But it's dedicated for sure also with the radial engagement. And when we test these materials and try to understand how the materials are working, then we make really a lot of internal tests. And I just show you here an internal test, because for sure if you go on a higher speed rate, then the wear will also been increased, but maybe you've been faster. So there's a lot of good and bad things you have to consider when you choose the right cutting data. And we did that these kind of tests, by the way, with our VXF12, which is a high feed cutter. I will show you later a little bit more about the tool. Very interesting that we use really here a high feed tool because of many reasons. It's easy to handle, and you get a very high performance out of this kind of tooling. Yeah, and you get really as a result then really here these kind of frames where you can play around with the feed rate and the speed rate. For sure, it gives you certain different tool life. So means if you have too high speed and feed, maybe the tool life is too low, but you have also a very high metal removal rate. Yeah? So you need to find really the compromise, what is best fit really in your application. That's the most important and challenging thing, because that can be not shown in a table, because it's dedicated to the environment outside of the tool. Yeah, yeah, coming back to the situation, speed versus temperature. It's a clear really focus that you have. If you increase the speed by constant feed rate, for sure, then you increase also the temperature. So that's easy to handle for maybe a turning tool, but for the milling tool, it's a little bit more challenging, as the milling tool is constantly going in and outside of the workpiece. Like you have a starting point where you have a very low temperature. Then when you go into the material, the insert starts to cut and is going through the material. The temperature is increasing and increasing more and more. And for sure, at that point, you are not able to really have a good coolant apply to the cutting edge, because for sure its environment is around the workpiece, and you cannot really have a good coolant. So it's internal coolant is mandatory at that point. And then if the cutting edge is coming out of the material, for sure it needs to come out somewhere. Then the coolant is going really to work much more, and for sure, as the air is also cooling down the cutting edge, you see the temperature is going down again, and then this process of heating up with the next round is coming again. This is the graph with dry machining, and for sure with wet machining is even more differences between the temperatures. And this is a challenging thing for the insert. Why? If we have a lot of high and going up and down with the temperature, also it's a very high risk of getting cuts into the material of the cutting edge. And therefore you have to be really completely understand how much heat you create during the cutting process. And that's not only given by the tool and the geometry of the tool, it's mainly also given by the radial engagement of the tool. We have here one example of the titanium. It's the same idea for every material. Yeah? It's not just showing you here the results from titanium. Means if you have a radial engagement of 10% compared to 50 or to 100%, you have a different amount of heat what you put in the insert. And means also that you can turn that idea also in speed rate. Means you can use that. If you have a very low radial engagement, you can increase the speed rate. If you have a medium engagement, you can have a medium speed. And if you have a full engagement, you have to reduce the speed. That's very important to understand, to handle that a little bit, because for sure on a live workpiece is that challenging if you don't have really a good CAD/CAM solution. We're trying to give you also some indications with formulas and with factors on it, but for sure that's only valid for straight machining. So if you have curves in your workpiece or in your directions of your cutter, then for sure the radial engagement is also changing. So it's very important to understand that you cannot have then the same speed rate. Effectively, you have to slow down if it's the inside curve, and when it's the outside curve, you have to speed up your tool. for sure that is challenging if you not have really a CAD/CAM system which supports you in there. Yeah, what does it mean really for stainless steel? If you look on the radial engagement and the possible speeds, if you look here on 14404, which is a 3016 here in that case, that would be the curve. Yeah, and you can really have with radial engagement of 100%, you can go up to 150 meters. But if you really reduce the radial engagement, you can increase the speed rate here. Yeah, that's very, very interesting and very helpful. Because then you can be much more productive and you can be faster, finish your jobs. The same idea behind just transfer to titanium alloys. For sure, the maximum speed here is much lower, yeah, and the curve is the same model and the same direction. I think it's pretty easy to understand. Yeah, basically, if you really understand how to choose the right cutting data, there's always a variability in, and you can react on that. Means that there's a window where you should play around, and that's dedicated not only from the tool and the geometry of the tool, it's from the radial engagement. Also, depth of cut is very important, because then you can increase your metal removal rate, although you're not increasing too much the heat. So it means it's always good on these kind of materials to have a very high depth of cut and use the tool as maximum, which also helps to support the wear from really over the cutting edges. So it's a very smart thing to look at that from that side. I want to show you also what we as WIDIA are doing, or what influence factors we can have from on the cutting tool, and what we provide you on really a best solution on that. Our main four playgrounds really to understand is the substrate, so the carbide itself, which has a certain alloy as well, and we can well play around with that and help you also to make the insert more heat resistant. Then we for sure have the coating, means the top layer coatings, which help to isolate the insert and prevent it from heat, increase the wear resistance because it's very hard, and also can reduce the friction on top of the swarf, because there is for sure also a movement process which prevents also the situation really to increase the heat. Yeah, for sure we have the macro geometry, means how the tool is looking like. If you look at the various milling tools, you understand what I'm saying. How the insert is laying here in the pockets, or how the cutting edge is formed really on the solid carbide ends. We have a lot of possible ways to really react on that. Just one sentence to that. On a solid carbide end mill, you have around about 4,000 different parameters just for the geometry where you can play around with, and can really find the best solution on it. 400 of them you can directly influence for sure by the angles, and the rest is coming then from the other angles. And for sure you have the influence to create the micro geometry, the edge prep, which have a very high influence on the cutting forces and the surface quality. Means really here these kind of the cutting edge, and it's dedicated to really to the right application, to the right surface quality, and for sure also on the depth of cut, the machining process itself. Yeah, then coming to geometry grades, what we have in our offering, and which can really help you really to get the best performance out of that, and that's dedicated to wear resisting and the toughness here in the feed rate. What is not shown here in that graph is a thermal resistance, which is a little bit sad, but we don't have more layers than these two ones. It shows up also that we have a very high heat resistance here with the WS30 and the WS40 PAM, which are really dedicated with these kind of materials. Means not that they're not working in other materials, but especially these carbides are really dedicated for very high temperatures. Yeah, especially the WS40 PM was especially designed for these kind of um, challenges, to have a very high heat resistance, have a very high toughness, and have at the same time a very high tool life and a resistance also for this thermal crack risk. And just here some pictures of the micro design of tests what we made internally. These are the thermal cracks, which are very dangerous, because if they are going on like that, then this complete portion of the cutting edge will break away, and for sure then you have a complete unstable situation on the cutting edge, and that will create anything just not what you planned. And so far it's very important to have, as long as possible, a form like that, to have the best situation. Yeah, going to the tooling. We have for sure also very much experience in the tooling, and we optimize our tools since years, really, for these kind of challenges. And one of the really best tools in face milling, what we can give to you, is the M1200 series. We have the M1200 in two sizes, so it means we have a big size with a 09 insert called M1200 without the mini, and then we have the M1200 mini with a smaller insert size. We have for both sizes, we have 4 grades, 4 geometries and several grades, really to make sure that we can cover every need of the application and the environment, really to make you really the best result on the machine. And we can use these inserts on 3 different tool bodies. Means we have a high feed position of the insert. So means the insert is in a position of 15 degrees lead angle. So we can use really this part of the insert and can go really extreme high feed rates. We have the 45 position, and we have the lead angle of 60 degrees for high and stable machines. So we are prepared really with a very universal system, but it means also that we can really focus really on every application very in detail, and can really give a very good solution really for every challenge on the machine. Just one case, which is just a few weeks ago, we had here a case on P6 material, and you see the problem is we have a very long extension on the machine here, and this must be face milled here. And the problem is also, which is usually for the M1200 a little bit challenge, we have here a shoulder where we machine again. It's a diameter 50 tool here. P6 material, as I said, 140 meters, 0.7, as we have the high feed insert here mounted with a depth of cut of 1 millimeter. Very interesting is also, I don't know if we can hear the sound, because that's a little bit challenging with our system. And but have a look also on the color of the chip, and also we made it as a small part, really as with slow motion, so we can see really how the chips are coming out of the cutter body. And for sure we are running dry here, because that's the first choice, always running dry, because then the step between highest and lowest temperature are not so big, and giving us a better performance. Just, I will start the video. That's a part of the slow motion. You can see easily how the chips are formed and flowing away. It's pretty ideal. Yeah. Then the next tool and solution is the shoulder mill VSM 890, 8 cutting edges, very straight, correct shoulders, very close to 90 degree, very big portfolio, also having 3 geometries, also for high temp alloys, for stainless, for steel, for cast, for aluminium. So it's very universal, but nevertheless, it's also very good on these kind of materials. We have a very positive design on the cutting edge. You might see it here on the pictures already. And just an example also from a customer where we're running against competition 180 meters on 143.07, which is 304. Feed rate 0.15, which is not very challenging for the tool. For most of the customers, that's a standard value for that, and very nice application as well. I will go a little bit faster through it because there's basically happening not too much. It's just milling, and this is very cool. The next platforms I want to show you is really the high feed platforms. Why? Because we have already used them in our laboratories to test. This is the VXF12 what we use in the laboratories for make the internal tests. But also we have two another solutions, which is a 6-edged M360 and solid carbide solutions, especially for these kind of stainless steel and titanium materials. So very interesting. This is a VXF12 what we use. We have it in 4 different sizes, various geometries, mainly for sure for these kind of materials. geometry is the first choice here. I get some comments that the video was not played. We have the challenge globally that we have a lot of traffic in the networks, and sometimes the networks are not fast enough to transfer it in every corner of the world. I can tell you my children have homeschooling as well. They complain about the same things. And we globally have about the corona situation, these kind of challenges. These kind of videos we will hope to show you also in our website. Coming to some applications really for the VXF, this is a very nice application of an aerospace part where we have really the smallest insert size used, nickel-based alloy, so the heat side of the turbine. And we can easily outcompete here our competitors. We have here more than 300% higher metal removal rate, so we're running more than 2.5 times more feet per tooth, and we have much more tool life. So we make the competition is just doing half a piece, half a work piece here, and we can make 4 work pieces with 1 cutting edge. So it's very high what we can improve here. Another case which is also very interesting was a bigger one, VXF12. It's a huge part. It's also somehow a turbine, but for sure a complete different size. You see this laying here on the street, and this is mounted on the measuring machine. And I will show you also this kind of machining process. I will jump also a little bit faster through that sometimes because it's a complete video. Now it's a huge turbine blade what we have to machine here, but also there we were pretty successful, and the competitor was really one of the best ones out of the market, I can tell you. Also the color of the swarf were extremely nice. Coming a little bit to the solid carbide section. For sure, we have as a first choice always to these kind of materials the variable families, which is sorted out by really a lot of products. Meanwhile, so we have really here 4 flutes, we have 5 flutes in various geometries. We have also the 7 flute, which is a very interesting product, especially for these kind of materials, because it gives you a lot of advantages, especially if you really are on dynamic milling already. Then you really have the chance really to improve your processes very much. And we are launching right now the new Variable Extreme as a 4-flute version. This is also a very interesting product because I can really tell you I made some experience with that, and it was really amazing to play around with that tool. But first to the variable 3, which is a 7-flute tool, and we have it since a while, but it's amazing what you can do. For sure, it's not dedicated for full slotting. Yeah, that's a tool really for dynamic milling, and just showing what we can do with that tool on a very easy stainless steel, but also just with air coolant. So it's a martensitic 1.4305. This video is also available on our homepage and on YouTube, so you can easily access it. But also boring, so we speed up a little bit and make it a little bit faster, just not to get sleepy, because face milling with a solid carbide end mill is pretty unusual, but it can be very effective if the machine is not too stable and you cannot really have a big tool on it. Then solid carbide end mills can be very interesting for it. Now we go down with a ramp angle of 0.5 degree, just to make sure that we have no problems with a 7-flute in a closed pocket, which is extremely nice. Also, we speed up a little bit because that's getting boring. But you see for sure that is the dynamic milling process, that way with eye machining from SolidCam, really to make sure that we have a full control about the radial engagement and really the cutting edges, which gives you really as a secret really the success here. Yeah, that is the Variable Extreme. Very nice product. The key features of that tool is we improved everything on a floor flute, what you can do. There's no straight edge on that tool. There's everything is we're resynced on that tool on every piece of geometry. It's extremely nice what you really can do. We have twisted end face, we have a parabolic core, we have a nonlinear chip gash profile. Everything is really curved here around the cutting edges. That's amazing what you can do. It's available from diameter 3 to 25, hopefully very soon. And for various versions of it. This is really nice what we can do, and during the field testing we made already some nice examples. This is mnemonic ATA. We have a pre-machined surface. It's also a turbine blade for a still standing turbine on the heat side. Also, we can really here increase the tool life. This is one of the main competitors. I don't say the name because we don't like to name that. But you know, the application engineer was also just taking the tool off from the competitors, put our tools in, and just nearly doubled the tool life. So it's very amazing. Yeah, coming to the next tool, which is out of the variable range. It's called 4U50 and 4U80 roughers. These roughers were really made for high temp alloys and stainless steel materials. So we have unequal flute space. We have really a complete optimized design, especially for these kind of materials. And we have really a very perfect solution for these kind of materials when you have really problem with long chips, where you don't are able to really get rid of the chip situation. Then you have here an option for really rougher profile tools. Yeah. One example also from there, this is also an aerospace part, a P5 steel material, and also the competition was really doing a good job, but we can increase it much, and we have really here a higher tool life, which was the force, just also by a higher metal removal rate of 50% more, and for sure giving the customer 86 additional machining hours on the machine means he can sell much more products of his series and really can increase his productivity massively with that tool. So very interesting. As I said already, we have already solid carbide high feed tools, especially for these kind of materials from diameter 6 to 25. And also that is very amazing what you can do. We had here an example. This is a motorsports part in titanium. So you see which kind of motorsport that is. That's Formula 1 parts. And we have to machine a cavity down there. That's around about, I don't know if you can see the picture, 46 millimeters, which is the maximum depth of cut here. and the width is 60 millimeters. So we have to machine this cavity from a full block of titanium material. And the competition did that with a ball nose tool, and the metal removal rate was not too high, let's say it that way, and the cycle time was also pretty long, and we can improve it to 6 times more metal removal rate, and the cycle time was for sure then just 8 minutes. Just to optimize it, we have also made a small video, but for sure this with titanium means we have a full coolant. Here you don't see anything really in the machining process. If you would hear the sound, you would hear it's extremely silent, and in the beginning we were not sure if it's even machining or not. So silent is the machining process here. And look at the clamping of the workpiece. It's just clamped here on the bottom, just a few millimeters, and without any vibrations. Very interesting. Yeah, what I need to consider really to choose the right strategy in these kind of materials, stainless and high-temp alloys. Generally, the influencing factors are for sure the tensile strength, hardness of the material, the machinability, ductility, heat behavior, and for sure it's always an interaction with the workpiece material, the cutting data, the tool, the machine dynamic, and the CAD/CAM system, and for sure the approach with the workpiece, not only the workpiece itself. Generally, this is a very common advices. You should use the feed rate compensation. You should choose the right cutting speed. Understand how to use the right cutting speed. The cutter size needs to be the right one to the application. The cutter position is very important. The cutter angle of entry. For sure, the cutter positioning itself, it's important. That really have a certain overhang at the tool. Use climb milling, negative angle of entry, avoid full cutter engagement. Don't do full slots with milling tools. It's never perfect for the cutting process. Not with indexable on the picture. It's the same for really solid carbide. And for sure, look at the pitch of the tool. Respect always the forces and the feed rate, how it's been compensated. Because for sure, remember the depth, the radial depth of cut is changing during the cutting process, and it's getting critical here at that point. And for sure, when you have really the areas where you get problems, these are the classical ones. Here at these corners, here you have this full slot situation where it's not nice. These corner situations here, when the material is going to be broken through, when the cutter is really going through the material, then you can manually react at that at least. I get the question here right now, which CAD/CAM software you prefer to machine the titanium in Inconel? And you know, there are a lot of products meanwhile on the markets who can really solve these kind of issues. I made a lot of good experience with iMachining from SolidCAM. Additionally, also S3 has a certain software support on that, but also others do have a good support. But it's a little bit tricky because some of these guys have a certain patent on the strategies, and it's also important to understand which kind of workpiece I have in front of me, because that's for sure also one thing which is important. And what's also important, CAD/CAM is not everything. Also, the machine has to follow these processes and passes the machine is calculating. And I see already on the market machines which cannot follow the program. So it means the program is faster than the machine, and then yeah, it's getting a little bit challenging with that. Though the important thing is to understand the complete process. This is very important. Yeah, also trapezoidal dynamic processes are very helpful. Also, sometimes you are able to program that manually. That's not always necessary to use a CAD/CAM solution for it. To prepare the corners, really optimization on the ways. for sure, CAD/CAM solution is helping there here massively, not to do that all manually. Also, if you look really on a closed pocket or really on pocket machining, also it's very important to have really a pre-machining to make it really easy for the tool, or you have really a CAD/CAM solution, like a plunge milling. You can have a situation, pre-hole drilling, or you really have corner loops, whatever. It helps really to avoid to have this full engagement around the tool, is helping for the process. As much as you need to understand, you increase heat massively, and as a material is getting more and more sensible, these problems are getting faster. That's always the message of it. Generally saying, it's important to have really a positive rake angle on the cutting edge. So means a positive tool, like here our M1200 or BSM 890, the solid carbide end mills. Yeah. Chamfered and hone cutting edge, because on the insert you can choose usually between that, called in our range usually GD or MM. This is the first choice usually in these kind of materials. If you look at the grade you should choose, it should be a fine grain grade, high wear resistance, high hardness, and with good properties even at high temperatures, and for sure at the same time also tough. So it's what ends up in WS40 PM usually. Yeah, and if you really go then for application hints, yeah, it's really that's what we. I mean, that is a summarize of what I was saying in detail the last 50 minutes. It's really respect machinability and heat reaction of the material. Though you need to look at the material, and titanium is not every time titanium, because there are several different alloys. The same for stainless steel. There's not just one stainless steel in the market. It's a really complete different setup if you have one 4305, or if you have a super duplex material. That is really different, like day and night. And so it's very important to understand what is expectable at these kind of materials. Yeah. Very important is also to have really a good tool which is having a low run out. If you have a solid carbide end mill, also look at the tool holders. So very often I see, well, they have the nicest tools on the machine, but the run out of the tool is so bad because of the tool holder itself. Yeah. The problem zone respect is very, very important, because if you have a recutting of chips, or you have problem zones where you get no control of, the complete process can be really running very good, but on these places you can destroy your tool immediately. Very important is also spread wear over the length of the cutting edge, means use always, as long as much possible, the length of the insert or of the cutting edge of the tool. Why? You spread also the wear around these cutting edge, means you get a higher tool life. If you just use a little bit of the cutting edge, it's worn here, and then it's done. Oh, sorry. And for sure, recutting of chips is very important. So a very important thing is, during the process, you need to get the chips out of the cutting zones. That is a very important thing. You need to have to look at that with coolant processes, or with machining processes, which gives you a certain really direction of the cutting edge, where we really can put the chips out of the zone. Usually it's helpful just to go with air. First of all, you see it better. Second of all, this kind of problem with the grades is not there, that you have really a problem with these heat shocks of the insert. And for sure with all of the tools, but especially with solid carbide end mills, use dynamic milling. Vari-mill family roughers are preferred. For sure, also if you have a flat topography, you should think always about X feed or a high feed solution, like our BXF families. Yeah, that's basically what I was preparing for the webinar today. As Isabel already said, we will have a second part, mainly focused on turning, grooving cutoff, and indexable drilling. that will be the second part. If you have interest really to understand a little bit more in detail, you can look at our information sources like our website. We have our digital cutting tool assistant, WIDIA Novo, where you can really find the right cutting tool. You can put in really your material and you will find the right solution for it. It's available also to download from our homepage. For sure, we have a contact based in Europe. We have it globally, but I just put here the European contact information in it, called Customer Application Service, where you can go in and really go in contact with the expert by mail, by telephone, or really also with a chat system. And for sure, you will find also a lot of information on YouTube and on the social media channels. Yeah, let me go through a little bit of the questions, what I can answer fast. So a lot of questions are already answered. Are there additional questions? So I answered already about the CAD/CAM software. There's one question which is pretty good. Yeah, thank you very much. Yeah, if there are no questions left up to now, feel free also to contact me, to follow us on our digital and classical ways, and yeah, let us also know if we can do something better. Oh, there's an interesting question which I can maybe answer pretty fast. It's the edge rounding help on end mills. So every sharp corner on a tool, on a cutting edge, is always a challenge. So means if you have a corner radius on the tool, it helps more than we have a chamfer or sharp edge. So because for sure wear is getting stronger on a sharp corner or on a sharp edge. That's a very important thing, and that's the reason you should also have a somehow rounded tool. So we have a question, SS40L. I'm not sure about really that material name, because that maybe is an American name or an Indian name. I'm not sure really. I would need to look about the material in detail, but you can easily enter that in our Novo system. Usually the great recommendation dedicated to the indexable milling stuff will be something like WS40 PM. How much does coating thickness impact tool life on superalloys? That's a good question, because it's not only the coating thickness which impacts tool life. For sure, that gives you a certain isolation on it, but also if you have a thick coating on it, you have a more round corner on the cutting edge. Means then you create more heat on that corner, and you cannot generally answer that question. That's a little bit a problem. Yeah. So it depends really on the cutting edge, on the superalloy itself, on the workpiece, on the cooling system, on the depth of cut, on all these factors. So generally, answer to have a fast answer to that is not really possible, and would be not easy to give. The answer SS40L is a stainless steel. Yes, as I said, that's really the best thing really to look really in detail. Then on our Novo system, you get a really good information on there. Generally, I would say something like WS40 PM will come out of this request. Rake angle should be recommended for stainless steel machining, like positive or negative rake angle. But the positive rake angle is the important thing. If you have a negative rake angle, then you have the problem. You have a lot of pressure. You create a lot of heat with that, and then you have really more problems than you solved before with the cutting. And so far, I can just recommend you some of the toolings, what you see already. They all have a positive rake angle. Negative rake angles are very seldom. Meanwhile, they are mainly used just for cast iron or hard materials. Usually on all steel and stainless steel and high temp alloys, the geometry of a very positive situation like we have on most of our tools is standard. On hard machining and cast iron machining, you would go for another tooling, which would also come out then from Novo. So far, I think I could answer nearly all of the questions. Then I would hand it back to Isabel again.
Yes, Mike, we don't have any more questions. So we thank you for joining this webinar. And as Mike said, join us in the second session because it is the second episode of today. And follow us on our social media channels because there you can find all the information about the next trainings, machining videos, machining tips, and more. So we are on YouTube, and as Mike said, Facebook, Instagram, VK, and Twitter and LinkedIn, all of the major social media networks. So we wish you a great day or evening, depending on the time of the day, and we will see you next time. Thank you very much.